Greetings to all of you who are joining us for today's hybrid seminar on safety, security, and safeguards by design for small modular reactors. My name is Noah Mayhew. I am a senior research associate here at the Vienna Center for Disarmament and Nonproliferation, and I will be moderating our discussion today. SMRs have been on the horizon for some decades now, though in 2025 the feeling seems to be they seem closer to operational deployment than ever. Once they are commercially deployable, SMRs and other advanced reactors have the promise to expand access to nuclear science and technology. By way of example, states that had never considered nuclear power for electricity generation before could find themselves in a position to tap this resource. SMRs could be accessible to states with smaller electricity grids and deployable in remote locations such as mines. There's also many other potential uses for these reactors, including water desalination, heating, steam for industrial applications, fertilizer manufacturing, and hydrogen production. In order to make the most of this potential promise, though, it is essential to ensure that SMRs meet current standards of safety, security, and safeguards, which brings us to the topic of today's discussion. The concept of 3S by design, which involves the comprehensive integration of these elements at every stage of the design process, is crucial for ensuring their effective, efficient, and mutually complementary implementation. It does not imply any additional obligations for the state, and incorporating these elements from the design stage could even reduce regulatory burden for the end user. Our speakers today will discuss 3S by design as it relates to advanced reactors, including as a follow-up to the IAEA's 2024 conference on small modular reactors and their applications. I'll introduce our speakers in a moment, but just first a few housekeeping announcements. First, please note that we are recording our speakers' initial remarks, but that we will not be recording the question and answer session that follows. Second, if you are joining us on Zoom, please use the Q&A function to submit questions. We will not be giving people the virtual microphone. If you are here with us in person, when I call on you to ask your question, please wait for one of my colleagues to bring you a room mic so that our online viewers can hear the question. Third, whether online or in person, we ask you to please keep your questions concise and to the point. We do have limited time, and I want to make sure that as many people who would like to take the floor have the opportunity to do so. Fourth, and finally, at the end of this seminar, we will be distributing a survey for you to fill out both online and in person. Please, please, please do fill it out. This helps drive our programmatic work in this area and helps us to get a better idea of what you got out of the seminar. So with that, I will introduce our speakers. We will start with Dr. Alexis Trahan, who is a safeguards technical specialist in the IAEA's Department of Safeguards. Dr. Trahan will discuss some of the outcomes of the IAEA's 2024 SMR conference, as well as the safeguards relevant considerations of SMRs and other advanced reactors. We'll then move to Dr. Carlo Arcilla, the director of the Department of Science and Technology at the Philippine Nuclear Research Institute. And he will also discuss his takeaways from the conference, as well as to give a member state perspective on 3S and SMRs. And then finally, VCDNP's own senior fellow, Dr. Sarah Case Lackner, will round us off with some analysis on safety and security interfaces and key challenges for SMR deployment concerning safety and security. So with that, let me pull up your PowerPoint. Dr. Trahan, I'm happy to hand the floor to you.
Perfect. Okay, thank you very much, Noah. Thank you, VCDNP, for hosting this seminar and for inviting me to speak with you today. I appreciate the interest in this topic, and I'm looking forward to talking to you, as mentioned, about safeguards by design for advanced reactors. So I'd like to begin to give us a reminder of safeguards themselves. So IAEA safeguards are a set of technical measures that are applied by the IAEA on nuclear material and activities to independently verify that all material is not diverted from peaceful activities. And states accept these measures, of course, through the conclusion of legal safeguards agreements. There are 191 states with safeguards agreements in force now. And so when we consider safeguards by design, it is simply the early consideration and incorporation of the aforementioned safeguards technical measures into the design process of nuclear facilities. And said much more simply, safeguards by design is simply good engineering design. It is also collaborative risk management. So it is acknowledgement that by not considering the safeguards technical measures early in the process, that there are risks introduced, that there could be additional cost when the reactor is built, and if safeguards technical measures require retrofitting. And so it's in a conversation that reduces the risk for the vendor, the state, and the IAEA. And I want to make sure to emphasize, as Noah said as well, that this is not, it's not a new requirement. It's not a requirement at all. Safeguards by design is a voluntary process, completely voluntary, initiated by the vendor or the state to basically incorporate these measures in their own design process of advanced reactors. And I will make the argument that safeguards by design results in more efficient and effective safeguards, and I hope to demonstrate that to you in the next few slides. So on that note, desired outcomes of safeguards by design. I'll go through a few as well as some examples. So as already mentioned, we know that a desired outcome of SBD is reduced risk to scope, schedule, budget, and licensing. In any engineering design project, the earlier that you consider the end-use requirements, the lower your risk in that project. And it's the same for advanced reactors. We also expect reduced operator burden. So to provide an example, consider a case where there is a material storage room in an advanced reactor facility, and per the safeguards legal obligations and agreement in the state where this is built, there is the need for a surveillance camera in that room. And perhaps it wouldn't have to be a surveillance camera. We could have a lot of inspector presence in order to meet the IAEA's verification requirements, but perhaps the operator and the IAEA agree that a surveillance camera is a better outcome. Now, if this surveillance camera was not considered during the design process, perhaps it has to be placed on a wall where there's no real physical access for the inspectors to the camera. There's no ladder, there are no stairs, and every time that the inspector has to come and pull data from that camera or physically access the seal, the operator has to build the inspector's scaffolding to get up to the camera. This is a case that is so easily avoided by having the conversation early on that the safeguards measures will include a surveillance camera and that surveillance camera will need to be accessible. And so reduced operator burden is a big outcome of safeguards by design. Additionally, the hope is there will be reduced need for retrofitting. So again, imagine that surveillance camera that the operator and the IAEA decide that it will be less intrusive to connect that surveillance camera to a remote data transmission system. But if that was not considered in advance, perhaps connecting the camera to that system requires drilling through a wall and for the cabling between the camera and the RDT system. In this case, this is retrofitting. Perhaps they will have to resubmit information for license review because of drilling through a hole or drilling a hole through a wall in this facility. And that's increased cost, it's increased time, and so can be very, very easily avoided by early collaborative conversations. And a last point of demonstration is the possibility of inclusion of joint or duplicate use equipment. So as another example of this, imagine an advanced reactor that is a pebble bed reactor, where there are pebbles flowing through and the operator will have a burn-up measurement system to measure the pebbles. Now, if this conversation is held early in the design process and the operator determines that the IAEA can also use that piece of equipment, they would need to install a second set of cabling to meet joint use requirements for the IAEA. Or it could be a duplicate use scenario where they install two of the same burn-up measurement system, one under the control of the operator, one under control of the IAEA. All of these outcomes make for more efficient and effective safeguards, but are really only possible if considered in the design phase. In the end, the IAEA will implement safeguards per the safeguards legal agreements, but with early consideration, there's chance to reduce the risk for everybody and result in more effective safeguards. As promised, I have some thoughts on safeguards relevant considerations specifically to advanced reactors, just to acknowledge a few of the topics that will be different from the current water-cooled reactors under safeguards. So one of the possibilities is the need for flowing fuel verification. Again, if considered early in the design process, then the IAEA can effectively safeguard flowing fuel. Size and space constraints. So as advertised, small modular reactors are small, and it's an economy situation. It's much more economical if they are smaller. However, inspectors will still need access to certain areas in the facility around the reactor for design information verification, for example. And if that is not accounted for, if that access is not accounted for early on, it could create just more time for inspections later when safeguards are applied. We expect new operating environments, as Noah mentioned. There could be advanced reactors at sea. There could be advanced reactors in extremely remote locations, in extremely cold locations that could place additional stress on IAEA safeguards equipment. And so, by considering these environments early on, the IAEA is better prepared. And I know at this point I'm sounding like a broken record, but this is the message that I hope that you take away, that the early consideration has a great number of benefits for all. We might see the need for different containment and surveillance approaches in some advanced reactors, where the water-cooled reactor maybe was sealed on a missile shield on top of the reactor core itself. Perhaps the IAEA seals in certain advanced reactor designs will be placed differently, and the earlier that's designed, the more effective and efficient the placement will be. We expect longer operating cycles from advanced reactors, current 12 to 18 months. We might see in the future 3, 5, even 10-year refueling cycles, and that does change the way that safeguards measures are applied, and certainly implies a heavier reliance on containment and surveillance. And lastly, though there are more, but the last one for today is novel fuel types. And so, flowing molten salt, molten chloride fuel is a new challenge for safeguards, and it's one that is absolutely safeguardable. We will implement safeguards as we always do, but by incorporating these thoughts early, it'll be better. And I just want to close by bringing up this engineering design point again. So my background is in nuclear engineering. Before coming to the IAEA, I spent many years designing and developing radiation detection systems. And so engineering design is my background. And when I think of safeguards by design, my mind just goes to good engineering design. Good engineering design asks the question, what are the specifications and criteria that your design must satisfy? One would never design a garage without considering what size vehicle needs to fit inside of it. So by simply considering the constraints, identifying where there are competing constraints, and analyzing trade-offs, the engineering design process is done better, and we expect better outcomes, a better product, reduced risk. And so I will leave you with that, and I really look forward to the discussion and questions. Thank you.
Dr. Trahan, thank you so much for those insightful remarks, and I'm glad to hear the repetition over and over again of this is sort of safeguards by design is a gift for the end user. Yeah, that's what it's meant to be. I'll immediately hand the microphone to Dr. Arcilla. So let me just switch this for you quickly, and just do that. Here we are. floor is yours.
All right. Thank you for giving me this chance. I apologize. I just arrived from Canada, so I might be incoherent, you know. But all right. I'll just skip this. There's a lot of interest in SMRs, and the main takeaway I want to point out, coming from an embarking country, is that there's an important need for building prototypes because there are 100 designs, but only 2 are operational. Too many PowerPoints, too few power plants. So regulators, especially as regards innovative design, need operational testing before it can be licensed for civilian use. This is obvious. And there's an urgent need to build prototypes so that reactors can be rolled out for widespread adaptation. I heard in a conference that with so much talk on SMRs, that the fuel now SMRs are coffee and paper, you know. So there had to be a creative licensing process to shorten licensing times without sacrificing safety. So is smaller really better? Of course, everybody knows small size, but again, from the end, what do you need it for? What do you need the SMR for? SMRs, when people talk about SMRs, people normally don't talk about the technology. They say it's just 300 megawatts and below, but there are many technologies 300 that you have to really consider. If it's an LWR reactor, we have more than 6 years experience, so it's no problem, but it's still possible to have LOCA on them. So you will need concrete containment and you will need the EPZs. Okay. So it will be easier to license if that's the case. Okay. But the principle remains multiple layers defense in depth. I mean, examples of this, of course, is the NuScale, and then the BWRX, which are about to be finished. Now, but advanced SMR technologies like molten salt and fast reactor are still largely theoretical. And here's the problem. With a lack of operational experience, the regulator, as I said, how can you regulate a piece of paper? You want to regulate a working plant. This is it. So you need significant R&D. That's why for molten salt and fast reactors, it will extend. My country wants SMRs, but there's no, where will you get it? There's no SMR to be bought off that. Now, fuel on the other hand, and this is a bias I have to say, has a lot of research already. You put the protection instead of in the building, you put it on the fuel itself. And there's a lot of experience in this, but only China has an operational fuel SMR reactor. There's none other than this. And the big promise of fuel is that if it works, you don't need to put the big concrete around it. 60% of the cost of a reactor is the concrete protection. So you can put it, if this is successful, anywhere close by here. But then limited operational experience is there. So there are only 3 operating SMRs. This is the Chinese one already connected to the grid. Okay. And Japan actually has an HTTR, but it stopped in Fukushima, but they have some operational experience. But it's just too bad that, you know, we don't get a lot more information from this. Fuel, you coat the fuel with several layers so that the protection is there. Radiation is prevented, but heat is allowed. There can be several variations, either pebble bed or you can have prismatic graphite blocks. Okay. But here's the big promise of SMRs, to my mind. There are tens of thousands of coal plants that are about to be decommissioned. Fuel allows high temperature gas reactors, up to 800 degrees. So theoretically, you can only replace the boiler of a coal plant and replace it with a small SMR, and then you can repurpose many coal plants. This is like what Holtec wants to do. Anyway, control rooms and nuclear plants are this. The Philippines is an old nuclear plant, but a nuclear plant, it might be refurbished. They said it will be like this. The advantage of this left side that it can't be hacked because it's not connected to the internet. So now, a few things about the Philippines and why do we need nuclear. So we have many earthquakes in the Philippines, but those are all the epicenters, but small ones. So only some islands that are free. We have volcanic eruptions. So this is the challenge of making nuclear. We have many disasters in the Philippines. We have the most typhoons, we have volcanoes, tsunami, earthquakes, floods, landslides, and the worst. You know. That's the last one that can be. So, but we have experience. Here's the first trisofuel, trigafuel subfuel reactor that was used from. This is a research reactor designed by female nuclear engineers. I'm very proud of this. It's now working. It was licensed 2 years ago. So, but why do we want nuclear? Because it's very expensive, electricity. 50% of electricity comes from coal, 90% imported in Indonesia, so we're really at the mercy of Indonesia. And we have a gas field that's depleting, and it's in the South China Sea, which is contested. And then there's a baseload backups. So you can see why we need nuclear and why we need also SMRs, because we have 7,000 islands. The islands are connected to the grid, will benefit from the SMRs. That's the driving point for this. Not climate change. We are victims of climate change, but it's for the islands that need it. 10% of the take-home pay of the median Filipino family goes to electricity. This is oppressive, okay? And you just study this. You can see that 9.5% of the take-home pay goes to electricity. So this is another reason why we want to consider nuclear. So, yeah. So, now, interestingly, just 2 weeks ago, an American company unveiled a small modular triso, not reactor, the thermal part. And I was there. I'll just show you. They made this reactor in 10 months. So they're building this. And they want to build this and license it in the Philippines. They cannot license it in the US because the licensing is very expensive and it takes a lot of time. We need more of this, prototypes that can be tested. So that's a trisofuel. These are advanced manufacturing techniques. They cannot license in the U.S. because of the time, and so they will try to put it in the U.S., in the Philippines. The thermal unit's done. I was there during the launching. Engineering hurdles are there, the thermal hydraulics, but it's good if there's a working model that we have. Okay. So the regulators have to streamline approval, then offer the financing models, but prototypes are needed. Because without prototypes, we will just be regulating pieces of paper. Thank you very much.
Thank you. Oh, yeah, please go ahead. All right, right over to Sarah. Dr. Case Lackner, pardon me.
That would be weird. Please don't call me that, Noah. So if that's your incoherent, I'm in trouble. But that's okay, because I like a challenge. That's why I like to speak last, and that's why I'm going to do this with no slides. No entertainment. You just see if I can keep your attention without that. What I'm going to do is I'm going to talk to you a little bit mostly about security by design, because I think We don't need to hear any more about safeguards after Alexis or after Dr. Arcilla has talked to us a bit about safety and examples. I think I'm happy to fill the remaining gap of just mostly talk about security. So I actually am going to steal from their briefings. That's why I like to go last. And the first thing I'm going to say, the first thing on my list of things to say is that it is really important to think about safety by design and security by design. And generally, people do think about safety by design. If you're building a reactor, you're very concerned that it will be safe, because if it's not, you've got a problem. No one wants that thing. Security by design tends to come in a bit later, like safeguards, but I'm going to use your, you had a great analogy about a garage. It is good engineering practice to build a garage that fits your car. That's good. If you know you're going to need safeguards, if you know you're going to need security, it's probably a good idea to think about that before you start building a massive engineering project, rather than afterwards trying to, oh, let's just paste that on, and ooh, that door is going to be a problem because we've got to leave it unlocked for the safety people to be able to get in case there's a problem. But we kind of have a really important sabotage-prone item behind it. Whoops. So you need to think about this early on. So I want to say practical. It is good engineering practice. It is a good idea. It just makes sense. But talking about SMRs, really, a lot of the safety and security considerations by design aren't that different from bigger reactors, especially security. Things are smaller. You need to think about that. But in principle, a lot of the ideas that you're going to be trying to implement are going to be extremely similar. I'll get to the ways in which they're different in a few minutes, but largely the main message, one of my messages I'm going to repeat is, it's a lot of similarities. They're just smaller. I think you mentioned this as well. They're just smaller. But that said, okay, and so let me say one thing first, which is, that means I'm going to be emphasizing this idea, which you've all heard before, evolutionary, not revolutionary. It's a little bit different, but you should still just be doing this. The stronger emphasis on passive safety systems. That's mostly because these reactors are new. I think if we were building big new reactors, everyone would be thinking more about passive safety systems than they did at the beginning. But it's good. This is a good thing. It's good that these SMRs are looking into putting in many more passive safety systems. Props to safety by design, because that's exactly what that is. The approach to an execution of security measures will also probably be about the same, though you can think about it a little differently. Now I'm going to get to some of the differences. If the reactors are really a lot smaller, it's possible that the radiological consequences might be less, and so you might be able to get by with less security. That will depend, and it will depend on your entire context of what you're building, where, and why. A lot of them also, though, have a lot more digital technology, so there you have some brand new security things that you need to be worried about. I know that you said these things are not connected to the internet. The problem with the world as it currently is that there's always a way. There's always a way. Wireless is everywhere. People bring their cell phones into reactor zones. People have pacemakers that are, by the way, they have communications protocols. There's all sorts of things that are happening now. It's not the end of the world, but you do need to think about it. And it's something that's best thought about by design. If you think about the digital systems in your reactor before you build the thing and then later go, oops, I didn't mean to hook up those two things together right next to each other where you can jump from one to the other, you're better off. So that's a security by design point for the digital side. You just need to know where all your digital check is going to be, where it is, how it's talking to each other, what are the different protocols, including in your safety systems, including in your safeguards. All of this needs to work together. And so I'm going to get in a few minutes, I'm going to talk about interfaces, because that matters a lot, not just on the digital side. So I'm being really, really general here, but the problem with making too many specific statements is that, as was also just highlighted for us, there are a lot of different designs in play. We're talking about different moderators, different fuel types, different sizes. SMR means just small. It doesn't mean one type of reactor, or even one power output. If you think about it, the microreactor designs are going down to 3 megawatts. The standard ones are 300. That's 2 orders of magnitude. That's enormous. That's a lot of difference. So we're talking about a lot of different things and tossing them all in a bin. But it doesn't necessarily always work so well that way. The other thing that's really different with all these different SMR designs are contexts for deployment. What are you going to do with them? You mentioned a little bit about this, Alexis, as you were talking. That matters a whole lot for your security measures. So, are you putting it in a populated area? Because that's different. Are you putting it up at the end of the world in the Arctic? Are you putting it in a mine? Are you putting it on a ship? Are you going to float it around just off of somebody's coast? And how are you going to transport it? All of these different contexts matter a lot for security. What is someone going to try to do to it? Are they going to try to attack it? Are they going to try to sabotage it? These are all factors, but there's no way we can make a generalization right now about all SMRs. It matters about what your plan is to do with it, and then you need to think about whether you're building the garage to fit your car. So even if you have to think about your safety and security and your safeguards all individually in different boxes, you really, and when you're talking about security by design, safety by design, safeguards by design, one of the great reasons you do this is to make sure you get them all together and that they aren't going to get in each other's way. And that you can use the different, the harmonization of them to build a better engineered project in the end. This is true for all 3S. I said that I'm really going to focus for a few minutes on safety and security to give you a good vision of what I mean when I say everything needs to fit together. So you need to ensure that safety and security are deconflicted in the sense that neither one gets in the way of the others. You heard my example earlier about a door that security badly wants to have locked and safety badly wants to have open. That's one example. That's a simple one. Even just very simple things. If you start early, you'll have an easier time of it later. I have a list here, which is why I keep glancing down. Identification of vital areas. What's a vital area? A vital area is a part of your plant that if it gets sabotaged, you have big, big, big problems. Usually your critical safety systems, good example. You want to know where those are so you can build the appropriate security systems around them without having to realize later, oh gosh, that was really important. I guess I'm going to need something to protect that. So that also applies to cyber attacks. That also applies to insider attacks when somebody in your plant has access they probably shouldn't have. All things you need to think about when you're identifying the critical vital areas of your plant, which are mostly safety critical. Cybersecurity, you should think about that. And why am I saying cybersecurity as a safety security interface? I think right now it's around 40% of currently operating nuclear power plants run digital instrumentation and control systems. It's not all of them. A lot of them are still analog. People seem to think that that everyone's running like the 70s and 80s, but it's not true. It's increasing. Those systems are not supposed to connect to the internet. They're not supposed to be hackable. This is good. You need to think about that. You need to think about what you're putting in, what kind of digital systems you're installing, and are they coming anywhere near your safety systems? So that's really important. Emergency preparedness and response, also really important. Law enforcement needs to do its job, and at the same time, emergency responders need to do their jobs. And they can't get in each other's way in an emergency where radiation is spreading. You need to think about that. And just offhand, there's things that aren't even about nuclear power plants. Making sure you have a good organizational culture, that's also a part of this. So you heard all of this. It's not really just for SMRs, but every single one of these things will apply to SMRs, and they're better off if you think about them before you build it, if you think about them as you're designing it. So basically, I'm coming back to the main point, which is this is all very practical. This isn't something that is, a theoretical policy thing, though it should be good policy, it should be good regulation. It's just, this is the smart way to design something that will be useful, that will be cost effective. So this wasn't really consistently done in the current fleet of plants, which is why we're all talking about this now. It would be good if people are going to build a lot more nuclear power plants to get it right this time and think about all these things that need to be dealt with beforehand. Now, Noah had also asked me to talk about stakeholders. And so I'm going to do that for about 1 minute before we go on to the more interesting part of this, which is when you all get to talk and we just answer. They were very interesting. Stakeholders. Look, my view is everyone is a stakeholder in the safe, secure, and proliferation-resistant operation of nuclear power plants. That's the public, that's civil society, that is everyone. Regulators, obviously, the public, governments. But who is necessary to make safety, security, and proliferation resistance by design happen? Well, first, the designers. They're the first line of defense. They need to be thinking about this. And the regulators. The regulators need to remind them that they need to do it, and they're going to have to show anyway that they're safe, secure, and proliferation resistant. So it would be a lot more practical to not have to go back and forth about this issue and just to do it from the beginning. The utilities will make decisions based on cost and effectiveness. That's their thinking. But the regulators aren't going to license a design that isn't safe and secure, and so it would be better if it got to be all those things at once. Safe, secure, proliferation resistant, cost effective because it got it right the first time in its engineering. It didn't have to be rebuilt over and over and over, losing money, running over budget, which is all a really long way of saying that the key players here in getting this done are the people who are designing, licensing, and building reactors. And of course, everyone else who is reminding them that this is really, really useful and should be done. So that was pretty much everything I had to say to you. Thank you for tolerating my lack of cool. That was a great video, by the way. This one. But tolerating that lack and really looking forward to the chance to answer some questions.
Thanks so much. Because all of you were so disciplined with time, we have plenty of it left. Before we move on to Q&A, I would like to just use my favorite 3 buzz phrases from each of your presentations. The garage for the car. You build the garage for the car, and I think that that is as true with safeguards as it is for safety and security by design. And so, as far as I'm concerned, that's one buzz phrase you should remember for the future. Regulating paper. The need, I love that as well, and it sort of speaks to this eternal question, seemingly eternal question on SMRs. Is it hype or is it here? Well, it's never going to be here if we keep regulating paper. So I like that as well. And then everyone is a stakeholder. You mentioned developers, and that's where my mind goes, but I also think that's true, as you indicated, talking across silos between these 3 disciplines to really make sure that they're not just deconflicted, but are mutually reinforcing. So with that, I will ask you to help me thank all 3 doctors at this table, and we'll move to Q&A.